Have you ever wondered why Earth has ice ages? Or why our climate has fluctuated so dramatically over hundreds of thousands of years, long before humans started impacting it? The answer isn't just down here on the ground. It's written in the stars, or more accurately, in our planet's cosmic dance around the sun. This is the story of Milankovitch Cycles. Welcome to Science Enigma. Today we're going on an astronomical journey to understand the massive, long-term drivers of Earth's climate. Forget what you think you know about climate change for a moment, because we're going back in time, way back. In the early 20th century, a brilliant Serbian scientist named Milankovitch proposed a revolutionary idea. He suggested that subtle, predictable changes in Earth's orbit around the sun are the main pacemaker for the ice ages. He spent decades painstakingly calculating these effects by hand. At the time, his theory was met with skepticism, but modern science has proven him right. So what are these cycles? They are actually three distinct, overlapping wobbles in Earth's movement. Let's break them down one by one. First, we have eccentricity. This sounds complicated, but it's just about the shape of Earth's orbit. It's not a perfect circle. Over a cycle of about 100,000 years, our orbit stretches from being nearly circular to slightly more elliptical or oval-shaped. Why does this matter? When the orbit is more elliptical, the Earth's distance from the sun varies more throughout the year. This changes the total amount of solar energy our planet receives. A more elongated orbit can mean cooler summers in the northern hemisphere, which is crucial. Why? Because if summers are too cool to melt the previous winter's snow and ice, glaciers can begin to grow year after year. This 100,000-year cycle lines up remarkably well with the timing of our major ice ages. Next up is axial tilt, or obliquity. You know how Earth is tilted on its axis like a spinning top that's a bit off kilter? That tilt is what gives us our seasons, but this tilt isn't constant. Over a cycle of about 41,000 years, it wobbles, shifting from about 22.1 degrees to 24.5 degrees. Right now, we're at a comfortable 23.5 degrees. When the tilt is greater, the seasons are more extreme. Summers get hotter, and winters get colder. When the tilt is smaller, the seasons are milder. Milder summers in the polar regions mean less ice melt, which again, is a perfect recipe for starting an ice age. It's not about the cold winters, it's about the cool summers that fail to melt the ice. And finally, we have the most complex wobble of them all, precession. Imagine our tilted Earth spinning like a top. As it spins, its axis slowly traces out a circle in space. This is called precession, and it happens over a cycle of about 26,000 years. This wobble changes the timing of the seasons. Right now, the northern hemisphere is tilted toward the sun in June, giving us summer. But in about 13,000 years, due to precession, it will be tilted toward the sun in December. Our seasons will be flipped. This affects how much solar energy different parts of the Earth get at different times of the year, influencing whether ice sheets grow or shrink. So you have these three grand cosmic cycles: eccentricity, axial tilt, and precession, all operating on different timelines, all overlapping with each other. Sometimes their effects cancel each other out, but when they align just right, they can push our planet's climate into or out of an ice age. Think of it like three different musical beats. When the beats sync up in a particular way, you get a powerful rhythm. In this case, that rhythm is a major climate shift. The 100,000-year eccentricity cycle seems to be the main beat, while the other two add complex harmonies that fine-tune the timing and intensity of glacial periods. Scientists have found incredible evidence for this in ice cores drilled from Antarctica and Greenland. These cores are like time capsules. The layers of ice contain tiny air bubbles that have trapped ancient atmosphere. By analyzing them, we can see a clear correlation between Milankovitch cycles and the historical levels of carbon dioxide and temperature on Earth. When the cycles favor cooling, the planet gets colder. Oceans absorb more CO2, ice sheets expand, and we enter an ice age. When the cycles shift to favor warming, the opposite happens. The planet warms, oceans release CO2, ice sheets melt, and we enter a warmer interglacial period, like the one we're in right now. Now it's crucial to address a common question. If these natural cycles exist, Does that mean humans aren't responsible for modern climate change? The answer is a clear and resounding no. Milankovitch cycles operate on geological timescales, tens of thousands of years. The warming we've observed in the last 150 years is happening at a speed that is completely unprecedented. The rate of CO2 increase in our atmosphere today is hundreds of times faster than the natural changes seen when coming out of an ice age. According to the natural cycles, we should be in a very slow, long-term cooling trend, likely heading toward the next ice age thousands of years from now. Instead, we are warming the planet at an alarming rate. We've effectively hit the fast-forward button, overriding the slow, gentle rhythm of the Milankovitch cycles with our own, much more powerful and rapid forcing. So understanding Milankovitch cycles doesn't absolve us of responsibility. Instead, it gives us a vital baseline. It shows us what Earth's climate is supposed to be doing. By knowing the natural rhythm, we can see just how dramatically our own actions are throwing the entire system out of tune. Milankovitch's theory is a beautiful testament to the interconnectedness of our planet and the cosmos. It shows how our world is shaped by grand celestial mechanics playing out over eons. It's a reminder that we live on a dynamic planet, constantly in flux. But it also serves as a stark warning. We are now the dominant force of change on this planet, and the future of our climate is no longer just in the hands of the cosmos, but in our own. Thank you so much for joining me on this deep dive into Earth's cosmic climate driver. I hope you found it as fascinating as I do. If you enjoyed this video and want to learn more about our amazing planet, please hit that like button and consider subscribing to the channel for more content like this. It really helps us out. See you in the next one.